All right, data types. We're just going to cover variables and integers in this video. We'll cover the rest in later videos. So, what are data types? So, regardless of your background, I'm pretty sure you've heard this statement everything is binary. Data types is just how we tell the computer or the compiler how to interpret those numbers in different ways. So, for example, let's take ASCII, which is used to store characters in C and also strings by extension. Uh, so ASCII is just one of the earliest text encoding formats, and it just said this number is going to map to this specific character. So 65 would be capital A, and 66 would be capital B, and so on. And if you want to look at the binary representation, it's going to be so and so, and each character is 8 bits or 1 byte. So yeah, so that's what a data type is. A data type is telling how you interpret different binary numbers as whatever you want to, right? Now, variables. Declaring and initializing variables. So, what are variables before we jump the gun? So, what are variables? Variables are just going to be named storage containers that you can associate with specific data types, and they can also be accessed and modified throughout a program. So declaring variables, how do you declare variables? You just say the data type of the variable and the name of the variable. And you can also declare multiple variables like so. What are you telling the compiler here? You're telling the compiler the variable is of so and so data type. You're telling the compiler the amount of space you require for that variable, which is inferred from the data type. Each data type takes a specific amount of space. And then you're telling the compiler the name of the variable that you'll be using to refer to it. Initializing variables. You can either declare and initialize separately like this, or declare and initialize in one go like this. The main point to note here is you never want to declare a variable and use it before it's initialized. That is going to lead to something we call undefined behavior, which is pretty self-explanatory in my opinion. Um, Essentially, you might just get a bunch of zeros or you might get a bunch of random gibberish. Point is, you don't want that. It doesn't make sense to do that, and you just shouldn't do that. You should always initialize a variable before you use it. Right. Let's take a brief tangent on memory on how things are stored. So, memory is organized into chunks of 8 bits or 1 byte. And each of those chunks is a location. And just like a location in real life, like say your home, they have an address called a memory address. So the memory address of the first byte of a variable or some data is going to be the memory address of that variable or data. And since we know each data type will take up a fixed amount of memory, we know how much space is going to be required to store that. So the memory address is going to be the very first one and not each and every memory address the variable uses, right? So let's take an example here. Let's say we have 12 bytes of memory. So we have 12 bytes from 10 through 21. Now let's take an integer, say 2025, and we have an integer that takes up 4 bytes and its memory address is 10 because it starts at 10. And then let's say a character A is stored. So A is stored at 14 and its memory address is just going to be 14 because it only takes up 1 byte. Note that the integer is stored in reverse. I'll get to that later in the integers part of the video. Okay, the built-in types. So we have integer and its variants, float and double, which is used for real numbers, the character, and void. We'll get to what void is later, but integers are used to store, well, integers. A float and double, as I already said, real numbers. Char is used to store a singular character, and then void we'll deal with later. So integers, duh, and then you have all these variants apart from just plain int. You have unsigned int long, 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 unsigned long, long, short, and short unsigned. So the unsigned variants are not going to store the sign, obviously, so they can only represent zero and positive integers. And in exchange for that, you get double the amount of integers you can represent because there is no sign bit. That bit is also dedicated to storing a value. And then you can drop the int, so you can just say unsigned or just long when you're declaring integers. For the plain int, obviously you have to say int. For the other variants, you can just say unsigned or long or unsigned long or short, right? So here's a few examples of integers. Nothing much here. And then here's the different sizes and ranges of integers. Note that I'm talking about 64-bit Linux systems here. But most POSIX systems will generally give you this range for integers, right? You need to worry about having different ranges mostly on embedded systems and stuff like that. Okay, how do you store integers? The representation is pretty straightforward. Unsigned integers are just stored as is, and signed integers are going to be in two's complement. Simple stuff. And endianness. As we saw in previously, like every int and the other variants of int take up more than 1 byte to store. So we have a little bit of choice as to how we arrange those bytes. We can have a lot of different permutations with 4 or 8 bytes, but it only makes sense for two ways, big endian and little endian. Big endian, you just take the big end and put it first. And little endian, you take the little end and put it first. First as in, it's going to be stored at the lowest memory address. So it's going to start with the little end and or it's going to start with the big end. Let's consider an example, right? Let's take a 32-bit integer, 1, 2, 3, 4, 5, 6, 7, 8 in hex. 32 bits is going to convert to 8 digits in hex. That's just because one hex digit is 4 bits. And in big endian, you would just store it as is. So each byte is going to be in order. So 1, 2, 3, 4, 5, 6, 7, 8. In little endian, it will be the opposite. 7, 8, 5, 6, 3, 4, 1, 2. Right? So most modern systems use the little endian format, but why? Why do modern systems use little endian? Let's consider the same example. So we have 4 bytes, the little end is here, and then the big end is all the way over here, right? Now let's try to add 1 to this. So you have a memory address, which is the first byte, and you're already there. So you just take it, add 1, and put it back. But say it was big endian. What happens now if you try to add 1? You have to go all the way over to the end and then take it up, add 1 and put it back, right? So most operations you perform on integers is going to affect the least significant byte the most and the and vice versa. That'll make sense once you think about it. Like most operations you do are going to just affect the smaller values more. Right? So that's why most modern systems use little endian. And that concludes this video.